Welcome back, everybody. Let's continue to talk about hypothesis testing. We already went through one example. Let's start the second. This second example is very similar to the first. In fact, it differs in only one way. The sample size in the first example was only 16. Remember I mentioned that that was an underpowered study. It was underpowered in that it was only based on 16 people, so it really wasn't able to provide much evidence for any difference that might exist. In this example, the differences that we see between the untreated and the treated people are exactly the same. It's still just a difference of 1 point on that depression scale. But you can see now it's based on 100 patients, so the sample size N is now 100. In other words, in this example, we have much more evidence because we have much more data. That means this example describes a study that is more powerful. It has a better chance of finding differences that actually exist. Let's switch the views and work on this together. Let's just remind ourselves of the basic scenario. It says on a depression scale, the population mean equals 26 and the standard deviation equals 4 for the population of clinically depressed patients. Higher scores represent greater depression. We want to test the efficacy of a new treatment. In other words, we want to see if it works. We select a random sample of 100 patients, so that's our sample size. After treatment, the mean depression score is 25, so the treated people do have a somewhat lower depression score than the untreated people. Our job is to determine why are we finding this difference between a sample mean of 25 and that population mean of 26? Is that a difference simply due to sampling error, or does that difference actually represent that this treatment works and that it lowers depression? Test with an alpha of 0.05 two-tailed. We did a two-tailed test with an alpha of 0.05 before. We'll use that again. Let's move on to step 1. Remember, we have two competing hypotheses. We have a null and we have an alternative. The null hypothesis always states no effect. We already know the population mean depression score for the untreated people. We're trying to find out via this sample of 100 patients, what's the population mean depression score for the treated people? So that's the value we are hypothesizing about. The population mean depression score, that's what D stands for the treated people, T. Based on the null hypothesis, the population mean depression score for the treated people is exactly equal to the population mean depression score for the untreated people. In other words, it equals 26. The alternative hypothesis needs to include every other possibility. So the alternative hypothesis states that the population mean depression score for those treated people is not equal to 26. Because those hypotheses are set up for a two-tailed test, it leaves open the possibility of finding statistically significant results in either direction. We could find that the treatment statistically significantly lowers depression, but we could also find that the new treatment statistically significantly worsens depression. Let's go ahead and move on to step 2. Step 2 is about finding the critical region because step 2 is figuring out how much evidence we need to reject the null hypothesis. Don't forget, we walk through these steps assuming that that null hypothesis is true. In the end, we might find enough evidence to overturn that initial assumption, but our initial assumption is that that null hypothesis is true. And in fact, when we create this distribution of sample means in step 2, it's based on the idea that the null hypothesis is true. And of course, when we create that distribution of sample means, it's based on these population parameters right there. So let's label up our distribution. This is a distribution of sample means. According to central limit theorem, the mean, the expected mean of this distribution of sample means will be equal to the mean from the parent population. So in other words, right there in the middle, mu equals 26. On that line right there, we are listing sample means, and right below it, we will list z-scores. A mean of 26 would transform into a z-score of 0. In this distribution of all possible sample means, there's some variability, and that variability is measured by the standard error of the mean. We need to know the value of the standard error of the mean in order to use that Z formula, so let's go ahead and compute it right now. The standard error of the mean can be found by taking the standard deviation of the parent population and dividing by the square root of the sample size, which is 100. The standard deviation from that parent population is 4, and we need to divide that by 10, so the standard error of the mean equals 0.4. What that means is, on average, the sample means differ from that true population mean of 26 by only 0.4 points on that depression scale. Do you see how in this example, compared to the example we did previously, there's less variability from one sample mean to the next? What that means is that this distribution of sample means has less variability than the one in the previous example. So any differences that we do see become less likely to occur just due to chance. All right, we've labeled up the distribution pretty well, but remember the reason why we're here is to locate the critical regions. We are using an alpha of 0.05 for a two-tailed test. That means we're going to have critical regions, otherwise known as rejection zones, on both sides of this distribution. Together, those two critical regions need to account for 5% of the distribution. That means in each critical region, on each side, there would be 2.5% of the sample means in that distribution of all possible sample means. We need to find what z-values mark off 2.5% of that distribution. So let's go back to our z-table and remind ourselves. We looked this up before in the last example. The area in the tail, which is this column right here, shows 2.5% right at this level, and that's with a z-value of 1.96. So the critical regions, otherwise known as rejection zones, are marked off at a z-value of 1.96 and at a z-value of negative 1.96. Those values represent how much evidence we need to find statistically significant results. Alrighty, now we're ready for step 3. If step 2 is all about figuring out how much evidence we need, step 3 is all about determining how much evidence we have. Because what we want to do here is transform our sample mean of 25 into a z-score. And then we'll figure out where in this distribution 25 is. Is 25 a sample mean right in here? The type of sample mean we would expect quite often just due to chance? Or, in this case, is 25 in this critical region, representing one of the sample means that we would not expect very often just by chance? Let's go ahead and transform 25 into a z-score. So for that sample mean x bar, we're going to stick in 25. Then we're going to subtract the population mean, which is 26. So that difference right there, that represents differences we actually see. And then we're going to divide by the standard error of the mean, which measures differences we would expect just by chance. And in this case, that value is 0.4. So we're left with negative 1 in the numerator, 0.4 in the denominator. Let's go ahead and crunch that out. We've got negative 1 divided by 0.4, and that equals negative 2.5. Negative 2.5. What that's telling us is that that sample mean of 25 is 2.5 standard errors below the mean. That's quite a bit below the mean. So let's plot exactly where it is. Here is a z-score of 0. Here is a z-score of negative 1.96. Negative 2.5 is somewhere within this tail, so we are indeed located within that tail. Let's just estimate that negative 2.5 is right about there. That's where our mean, x bar, which equals 25, is located. And you can see we clearly are in the critical region. We are in the rejection zone. And that provides us with the answer to that first critical question that I need to ask you. Is our sample mean inside the rejection zone? And the answer clearly is yes. I'm now going to ask 3 follow-up questions. And the good news is all of the answers to those questions will be the same. They will be yes. So if you walk through examples like I am right now, you'll be able to interpret your results very easily if you use these little tricks that I'm teaching you. So we concluded for that first question, yes, we are in the rejection zone. My next question is, should we reject the null hypothesis? Yes, we should. So I'm going to reject it. I'm going to X it out. and I'm going to check off the alternative. I'm going to embrace that alternative hypothesis. And let's actually read it just to get a sense of what's going on. The alternative hypothesis states the population mean depression score for the treated people is not equal to 26. And we have evidence that it's lower than 26. So we have evidence that this new treatment lowers depression. Here's my next follow-up question. Do we have statistically significant results? Yes, we do. So let's make a little note of that. We'll say that it's significant. And then my final follow-up question, sometimes it's a killjoy type of question. The question is, hey, is it possible that we're making a type 1 error? And the answer is yes. In this case, there is at least a possibility that we're making a type 1 error. Remember, type 1 errors are when we conclude we have statistically significant results and we are wrong. Remember, in this distribution of all possible sample means, it is indeed listing all possible sample means when the null hypothesis is true. In other words, sometimes we will find sample means this small just by chance, just due to sampling error. But we need to be reasonable. At some point, we need to draw the line and say we have enough evidence. We need to draw the line and say we have effectively ruled out sampling error. And that's exactly what we're doing in this example. What is the probability that we're making a type 1 error? If we use an alpha of 0.05, then at least theoretically speaking, the probability of making a type 1 error over the long run is 5%. All right, we're almost ready to interpret our results at step 4 and write them out very formally. But before we do, let's help ourselves out. At some point, we're going to need to say something about the probability of finding our results just by chance. And we're going to have to pick between the probability being less than 5% or the probability being greater than 5% of finding our results just by chance. And I want to remind you, area equals probability. We found that our sample mean was in this small little area. It was in that small rejection zone. So when we write up our results, we should list a low probability. Well, what's low? A probability less than 5% or a probability greater than 5%? I hope you can see that what's small, what is low, is a probability less than 5%. All right, within all that information you see right in front of us, we have everything we need to write up our results. Let's do that next. At step 4, we more formally write up our results. And there are really 4 things that we need to accomplish. We need to say what we're going to do with the null hypothesis. Are we going to reject it or fail to reject it? We need to interpret our results in everyday language. We need to show how our results would be summarized in a journal article. And we also need to compute the appropriate measurement of effect size, which in this case is Cohen's d. So based on the work that we've already done, we concluded that we are going to reject the null hypothesis. And here's how I would put that into context. I would say that that sample mean of 25 was within the critical region. This sample mean is unlikely to be found by chance if the null hypothesis is true, so we reject the null hypothesis. In everyday language, what did we find? We found that the new treatment statistically significantly reduced depression. Now we need to summarize how this statistical test would appear in a journal article. When we computed the test, we found a z-value of negative 2.5. So we start off by saying z equals negative 2.5. Then we need to say something about the probability of finding that result just by chance. And the probability of finding that result just by chance is very small. So we say p less than 0.05 based on a two-tailed test. The next thing that we need to do is include a measurement of effect size. So far, we've simply concluded that there is a statistically significant effect. We've concluded that people who are treated do have lower depression scores. But how much lower are their depression scores? It's true that their depression scores are 1 point lower on that depression scale, but most people probably aren't familiar with that particular depression scale. So what we want to use is a standardized measurement of effect size. That standardized measurement of effect size, Cohen's d, will tell us how big the difference is in standard deviation units. So Cohen's d counts in standard deviation units. That's something we can all more easily understand. In this case, our sample mean equals 25, And that population mean for the untreated people was equal to 26. So that was a difference of -1. We divide that by the standard deviation on that depression scale, and we can remind ourselves right up here, sigma equals 4. -1 divided by 4 equals -0.25. In other words, the people who have been treated, they have a lower depression score. How much lower is their depression score? Their depression score was reduced by 1/4 of a standard deviation. That's considered a relatively small effect. This might help you put that into perspective. One way that I help students understand Cohen's d is by comparing the effect size to differences in IQ scores. We've gone through lots of examples with IQ scores throughout the semester, so you should be pretty familiar with them. What we're talking about here is a Cohen's d of 1/4 of a standard deviation. Let's put those in IQ terms for a second. We know that an average IQ is 100 and the standard deviation equals 16. So the effect that we found here, where depression scores were lowered by 1/4 of a standard deviation, it's kind of like finding a difference between an IQ score of 100 and an IQ score of 104, because 4 points would be 1/4 of a standard deviation. And then in your own mind, you can get a sense of how large you think that effect is. Is there much of a difference between a person who has an IQ of 100 compared to an IQ of 104? That's something that we probably wouldn't notice if we were talking to two people, one with an IQ of 100 and one with an IQ of 104. There is indeed a difference, but it's a difference that's relatively small. All right, well, that concludes our second example. In this example, we had more data, more statistical power, and we found a statistically significant effect. I hope these examples are becoming more comfortable to you. We've got 2 more to do. I'll see you in the next video. In the meantime, be safe.